structure. I had a pen that worked. It would. All right, this is on magnetism. And this will be the last chapter for exam 3, which will consist of chapters 18, 19, and 20. So magnetism. All right, in the previous chapters we dealt with electricity. All right. And with electricity, we have protons, which are plus, and electrons, which are minus. And they have a charge of 1.6 times 10 to the minus 19th coulombs, plus or minus, depending on whether it's a proton or electron. And so we can have a static charge, again, electron, or if we have a proton in the center, and we have an electric field, like so that we did, which means if I put a positive charge here, it goes out. So we have single charges. All right, and then if we look at the electric field of, say, what we call a dipole, plus and minus, this is what the electric field look like, right? And a positive charge will go towards that. All right, so that's electricity, electric field. We dealt with currents and such. So that was the basis of basically chapter 18 and 19. 18 was static electricity, 19 was current electricity. Chapter 20 is a more, I should say a more almost mystical type of phenomenon, magnetism. And magnetism is sort of a great unknown for a lot of people. Is the fact that it's always an action at a distance, very much. You have a magnet, such as a bar magnet from the lab, from the class. A bar magnet has a north and south pole to it. And so if you look at a magnet, we're talking about a magnet. We go back to the original lodestones. And lodestone is actually made of magnetite. And I'm not going to get into that. That was part of that. But it was a material, a rock or substance, that would attract certain types of metals, such as iron, a compass needle. It would have a tendency to attract it. And then what it was found is that putting a compass, like a needle, on a lodestone, you can actually get it to follow the Earth's magnetic field. And the way you do that is by getting this little needle, put it on a lodestone, which is not know why it worked. Put it in a cup of water, and if you look at it from the top, so it just sits on there, it would turn out that the needle would point in the direction of the Earth's magnetic north pole, and the other would point towards the south pole. Again, we weren't really sure why, but that seemed to be the case, that it would point north. So this turned out to be a useful compass, meaning a way for finding direction, right? If you were out in the middle of the woods and it's cloudy out, how are you going to know where you are? I've had that more than once. A compass is what tells you where you are. So we go back to the thing of magnets, right? A magnet has what we call a north and south field to it. And it turns out that if you put it in iron filings, like we have in the text, right? The iron filings will line up like so, right? This looks exactly like our type of field for a dipole charge, where you consider the plus being at north and the minus being the south. However, unlike, say if you have positive charge itself, we can never get a compass to have a field like this, right? This is what we would call a monopole, meaning we just have a north pole. We can't do that because you would think intuitively, oh, if I just take a north-south, cut it in half, I'll end up with just a north pole. Well, if you take a compass, as probably most of you all know, take a compass, cut it in half, you'll end up with two magnets, one north and south. Break it up more, you'll end up with just still that. So the compass, it's not just a north pole to end and a south pole here, but it turns out it's the entire material itself. And this is all part of what we call ferromagnetism, or ferromagnetic. Ferro is from iron, so anything that has this sort of this magnetic type of materials. All right, so that's the first part there, is chapter 20. Now, if we look at the Earth's magnetic field, and if you look at it from the text, right, the Earth has a magnetic field too, and what we'll see is the Earth's magnetic field doesn't quite point at the exact North Pole. If we sketch out the Earth's magnetic field, you look at the Earth, all right? Let's take it with the A. So this is true north, all right? So this is geographic North Pole, South Pole, and the way you can find that is Polaris, right? The North Pole, the geographic North Pole is directly above Polaris, more or less. However, the Earth's magnetic field is not so. It's actually somewhere in northern Canada, the Earth's the magnetic North Pole. So we actually have a thing looking like this, right? So they're not quite exactly the same. And so what this means is, on a topographic map, right, like this one, there's a thing called declination. And what this is declination is the difference between what we call true north and magnetic north. And in Bemidji, northern Minnesota, it's approximately 3 degrees or something like that. It's been changing over time. It's moving slightly, and we'll get into that. What creates the Earth's magnetic field? It's been quite a phenomenon, trying to understand what the Earth's magnetic field is. Again, if you took, if you had any geology, we have not been able to penetrate anything more. I mean, the Earth is 6,000 miles, 8,000 miles in diameter, and we have only been able to penetrate about 20 miles into the Earth's crust. So we have absolutely no direct evidence of the interior of the Earth other than what we see from it, earthquakes, rocks have come up in volcanoes and such. So that's what we have there. So that's the angle of Earth's magnetic field. Part of this, we'll be dealing with this more when we do lab 6, which will be on magnetism. All right, that'll be coming up next, sometime later this week. All right, so what is a magnetic field? All right, we have electric charge. We know protons and electrons. But what is what makes a magnetic field? All right. What makes a magnetic field? Well, it was turned out back in about 1800 that when they first were able to create currents, and if you have a battery with a wire and create a current in the wire, what it turned out is that a compass would be deflected perpendicular to the wire. All right, so what does this mean? Well, it turns out that this current is actually producing a magnetic field. Current produces what we call a magnetic field, and we use the letter B for that. There's also M, but for the most part we use B for magnetic field, and we'll get into that in a minute as far as that is concerned. All right. So okay. Yep. So the way this works, if you point your thumb in the direction of the current, your fingers will curl around in the direction of the magnetic field, looping around it. So I can look at it this way. If the current is coming out, then the magnetic field loops around like so. All right? So B will be looping around, and so if I have a compass, it'll point in either, depending on the direction of the current, either point this way or that way, but it'll be perpendicular to the wire. All right. So, moving on here now. All right, so moving on. For electric field, the units of electromagnetic field, I should say, is the Tesla. All right, that's what the car is named after. It's actually named after Nikola Tesla. It's not named after Elon Musk. All right, so T, it's in units of Tesla, which is actually a very high magnetic field. So because of that, we have also introduced another unit called the Gauss, and it's in units of G. You may have heard of this. And 1 Tesla is 10 to the 4th Gauss. And we have this number. So this is the SI unit, or the MKS unit, is a Tesla. The Gauss is a smaller one because the Earth's field is about 0.5 Gauss. So it's about half a Gauss. So that's how we have that. So a Tesla is actually a very large magnetic field. It's extremely large. And the way we produce a magnetic field is by a current. A current, a moving charge produces a magnetic field. Not a stationary charge. You have to have a current. You have to have a moving current for an electric charge to be done on that. All right. Now, we're going to skip section 20.3, which is force on wire. So we're going to skip that, because then we're going to look at what is the effect of a magnetic field on a charge. And we'll also be dealing with this as part of a lab. We talk about that. I've got a lab which we'll talk about later. And we'll get into this later on. So that's the units, Tesla, Gauss, but no units are there. So let's see here. Oh, yeah. Okay. So what do we have here? All right. So how do we calculate? So I'm going to jump around a little bit here. So skipping 20.3, I'm now going to do section 20.4. And this will be, if I have, say, a magnet, north, south, and I shoot, and I have an electron or a charge, say a proton, it could be an electron, a charge coming out, and the magnetic field will go from north to south. We're not really worried about direct where it goes left or right. But what will happen in here is if I have a moving charge in a B field, then it experiences a force perpendicular to V. So it's moving charge with some speed V and B. Meaning if the charge is coming out, the magnetic field is that way, it'll be deflected either up or down, depending on the charge. So it'll be deflected perpendicular. Notice how this is different from electric field, electricity. We dealt with electricity, we have electric current plus minus. Electric current goes, electric fields that way, put a positive charge here, and it goes flying to the other side. They're all in the same direction, but in magnetism, everything's perpendicular to each other. So this would be, so a moving charge, it has to be moving, it cannot be stationary, it has to be moving. If it's moving in a magnetic field, it'll be deflected perpendicular to both of those. And the force that it experiences in newtons is the charge Q times the speed in meters per second, where this is in coulombs, times the B in Tesla, where all three are perpendicular to each other. The charge times the speed times the magnetic field will be the force that that thing experiences. All right? And so it'll be perpendicular to that. As we'll see with the lab, it turns out then that if we have a moving charge, right, so it's perpendicular to that. Doesn't slow it down, it just moves it perpendicular. So what does that mean then? All right, in this case, we just have a little horseshoe magnet with it going through, and that's it. What if we can have a bigger magnetic field? I'll leave that up for a minute. What in this case, we have a bigger magnetic field. And what we'll do is have a symmetry book, and this will be so we got B going in. All right, and I'm going to use this. All right, and we have suddenly a charge comes, let's use an electron, comes into this magnetic field. It will be, the magnetic field's going in, V is that way, it'll be deflected downwards. Which will be, meaning it'll be pushed perpendicular downwards, then side, and so on. It'll be actually deflected into a circle. Because as it goes, it gets deflected, perpendicular, so it'll go into a circle. And the radius of this circle, R, is given by the mass of the particle, in this case, this could be an electron, times the speed of it, divided by Q and B. So this will be the mass in kilograms. This will be the speed in meters per second. This is again the charge in coulombs, and this is the B field in Tesla. We'll get a radius of in meters of R. Now notice there's a few things about this. First of all, the faster it's going, the bigger the radius of curvature. The larger the mass, the bigger curvature. So what you could actually get out of this, if I have an electron, it's going to be relatively slight circle. But if I instead have a proton, well, first of all, it'll be deflected the other way. If I have a proton, remember a proton is 1,800 times mass of an electron. So it's extremely massive. In that case, it's because the charge is the same as both, because it's much more massive, it's actually going to turn out to be very hard to deflect this thing. Instead of a tiny circle, it's going to be barely deflected at all. So it'll have a very large radius of curvature. This concept is what we're going to use for what we'll see in a little bit, the principle of a mass spectrometer. And I'll get to that in a little bit. All right. So this is section 20.4 still. Okay. So we'll get into that. All right, so leave that up. Again, comparing this is the radius of curvature, depends on mass, the speed, the charge, and the magnetic field. Again, we'll be doing a lab that actually will do with all these concepts. All right. All right, before we get to that though, and this will be the last section to cover, before I get to that, I will talk about if we have a wire and we produce a magnetic field around it, B, and it's due to some current I, what is the value of this current, this magnetic field? what is the size of this magnetic field out here? Because that's partially what we want to look at too. Again, the Earth's field is about half a Gauss, which is about 5 times 10 to the minus 5th Tesla. All right? Because again, 1 Gauss is 10,000 Gauss is 1 Tesla. So 1 Gauss is about 10 to the minus. So 1 Gauss is approximately 10 to the minus 4 Tesla. Okay? So if I have this wire and I have a current coming out, what's a magnetic field? A distance r away. Well, it turns out B is given by this expression, mu naught times I over 2 pi r, where mu naught is given by the number 4 pi times 10 to the minus 7th. And I'm not going to deal with the units. The NKS is that. So that's what the field. So it goes down, decreases with the rate distance from the center. So let's do one example. Let's say I is 10 amps, which is a pretty good current, and R is 10 centimeters away. Well, let's make it 10 cent, which is 0.1 meters. All right, so about 10 cents. So it's about the right scale. And so what would B then? B would be 4 pi times 10 to the minus 7th times 10 over 2 pi times 0.1. This cancels out to give me 2. All right, that's 0.1. This will be 2. Let me see here. So that would be 100. 2 times 10 to the minus 5th, or about 0.2 Gauss. So this kind of field produces about half the, so a current of 10 amps, which is quite high, at a distance will produce a relatively weak field. Part of what we'll see is, if you look at the video and the quiz, currents of fear, which actually is a frontline program from 1995, which I have a video of it and a quiz with this. This goes back to the time where it was thought that do magnetic fields cause cancer? Do power lines cause cancer? Because we'll see they actually produce magnetic fields. So anyway, so this is all we're going to be doing here as far as that. One thing about it, if I have a current coming out this way, produces a magnetic field like that. If I have another one coming in, going that way, it produces a magnetic field this way, equal and opposite currents, B is 0. They'll cancel each other out. So I have a current coming out and a current coming in, the magnetic field will be 0. Sometimes you do this by having wiring going both directions if you really want to eliminate a magnetic field. So that's section 20.5. All right? As far as that. So this is our expression. B is mu naught I over 2 pi r, where mu naught is this number here. And that's the Greek letter mu. I'm skipping 20.6. And then I'm going to do a little bit on, so this is for a straight wire. So I got 2 other things here that I'm going to have as far as other ways to produce magnetic fields. So that's that part. leave that up. And then move into 20.7, 20.8, and then the final section. All right, so for 20.7, this is what we call a solenoid. All right, you'll see this when we do the lab later on, but a solenoid, and of course I don't have one here, but we'll get one later. A solenoid is just a long coil. All right, just a long coil with a certain number of, so if N is the number of turns, and L is the length, then N, which is turns per meter, will be N over L, right? So this would be number of turns, this would be a length in meters. That's what our expression is there. So inside, because it turns out, again for a wire, magnetic field loops around. But what turns out in a solenoid, we call a solenoid, the magnetic field is actually inside a long one. B is constant. And as long as you're inside the solenoid, it'll actually be constant and parallel to the axis of the solenoid. So B will be constant, and the expression for that will be given by B is mu naught. There's our mu naught again. N I over L, or B mu naught N I, where N is the turns per meter, I is the current in the wire, in the coil. So that'll be the magnetic field in it, and it'll be constant inside. You'll see this is actually a principle between MRI machines, because you use this basis and then change the magnetic field slightly inside to get it to respond for measuring material inside human body. All right, so that's section 20.7. So while I'm on that, I'll do 20.8. And if we have, instead of a long coil, we have a single loop. So one loop, and we have a current N, current I, and the rate, and it's, so we have just a current in one loop, one turn. Then the current inside, the B inside at the center will be given by mu naught I over over 2R. And we're not going to do any problems related to this. So this will be the standard. So we're only going to be really dealing with this one. All right. So this is section 20.8, which I'm only going to do conceptual wise. Problems will be either a solenoid or a long straight wire. All right. Last section I'm going to do here, and this will be, well, pretty much I'll skip 20.8, but the last section will cover will be for 2011, and this is a mass spectrometer. And what this is about are a couple things here. Example are, you get into chemistry, there's uranium-235 and uranium-238. Now we get into nucleus, and then we have carbon-12 and carbon-14. Now, these two are related. Carbon-14 is related to radioactive decay of once living things. I'm not going to get into this, but it turns out carbon-14 is what we call radioactive. It decays. It actually decays to nitrogen-14, which we'll get into. But these two are identical chemically. All right, now carbon-14, it's somewhere in the order of 0.1% of carbon is carbon-14, about 99% plus is carbon-12. But if they're chemically identical, how do you separate the two? Same thing here. Uranium-235 makes up 1%, uranium-238 makes up about 99%. These are two chemically identical. For a bomb, as we'll see when we get into, you need 235. Uranium-238 won't make a bomb, won't do that. If you even want to have a nuclear reactor, you have to have a much higher percentage of this compared to that. But they're chemically identical. So how do you separate the two? I mean, you're not going to go and grab one atom at a time. I mean, I suppose you could, but it'd take about 10 jillion years to be able to get enough to do anything. So the way you do this is with taking difference. Both of them are same, but this one weighs slightly more than that, and this weighs slightly more than that. So the way you do it is you take a mass spectrometer, and this is actually the basis of the Manhattan Project in 1940s for building the bomb, was trying to separate these two. I mean, fortunately, it's extremely hard to do this. Fortunately, we'll see how you do it, right? I mean, there's some other ways of separating, but for the basis of this chapter, what we have is we have our magnetic field. Let's say it's going in, and we have our both uranium, so uranium-235 and uranium-238. All right, so the 235 will go and be deflected if you have a big enough field, like so, and comes out. The uranium-238, on the other hand, I'll put it up here, 238, because it's slightly heavier, will actually be slightly less deflected. So what we'll have is, we can have a little bins here. So this is where the 235 goes in. This is where the 238 goes in. Now it's actually far more complicated than that, but basically that's the principle of it. So because it's curved, you just collect it. Now you do this process over and over and over, you can get a very high percentage. But that's the basis of mass spectrometer is to separate differently. And these are what we call isotopes, because they're the same element, but this case has three more neutrons than this one, and we'll get into that later when we talk about that, if you're not already familiar with neutrons and isotopes. So again, they're chemically identical, and this is how we do it. We take advantage of the fact that, again, R is mv over qb, so if it's slightly more massive, it's going to have a slightly bigger raised curvature. So this is the principle of a mass spectrometer, or mass spec, as we call it, and that's the principle there. Okay? So we can use that to separate 235, 238. So whichever one is heavier is going to be deflected less. So that is the principle. That's chapter 12, chapter 20, I should say. As far as that's concerned, we're not going to do anything on ferromagnetism and other things. So that's it. I will be doing a review for exam 2 on chapters 18, 19, 20 before the test. So have a good